This is starting to feel a bit like Groundhog Day. This is now the third time I've done this intro talking about what this machine is, what this drive is, and why I'm so excited about it, but the fact of the matter remains that I'm still doing this intro because it's all still broken. This is my PDP-1144. It is the last non-LSI PDP-11 ever made, which means it's chock full of 7400 series logic chips and AM2901 4-bit bit slice ALUs. It's a pretty dramatically cool machine, and I really want to plug this drive up to it. This is a Fujitsu Eagle hard drive, has 10.5-inch platters in the most epic sci-fi looking arrangement ever, but, well, the reason I'm still doing this is because we can't test any of that out because we can't get the power supply on this thing fully working. We got pretty close in the last episode. There are 6 power rails on this power supply. It's actually built kind of like 2 separate power supplies. 3 of the rails are +15, +5, and -15 for the logic. Those 3 are coming up fine. They've been working perfectly since we started this whole ordeal that we've been going down. The other half of the power supply is generating +12, +5, and -12. These 3 rails are dedicated to the memory, and these 3 have been giving us some grief. In the previous episode, we actually managed to get 2 of those up. We got the +5 and -12 up, but that last +12 is really starting to elude us. So we're gonna dig in deep to the +12 today. There's some pretty basic stuff that we want to check right off the bat, and then if that doesn't do it, we'll just keep digging into it. I'm not doing another one of these intros. I'm tired of doing these intros. So the next time I do an intro for this machine, it will be working. So that means that we're gonna get the power supply fully working in this video. I absolutely promise it, not because I'm clairvoyant or know the future, but because this footage will never see the light of day until that power supply is working. So I'm just gonna pull this out, put it on the table, and get to work. Let's go ahead and get the memory voltage module out again. I'll just remove the screws holding the 300 volt DC flat cable in place, then unscrew and remove the grounding cable. Then it slides right out the front, and with it on the bench, I'll remove the 2 mounting screws, the 2 capacitor screws, and the 3 transformer screws. And then the whole thing splits into and gives great access to pretty much all of the junk inside. And we're getting +35 volt generation correctly now, but each individual regulator has its own fuse. So let's start with the most obvious and work our way down to more complex, difficult areas. The fuse in question is F1 here, which is a 5 amp fuse. And after finding it on the PCB, I'll check it with the multimeter. And yeah, that's not looking right. I should be seeing 0 ohms instead of whatever that is. It's in a tough spot to get to, and it doesn't look like your traditional fuse, but the probes are definitely on it. It's a little, as we would say in Japanese, ayashi. So let's pop it out and see what's what. I'll just add some solder, then use the iron itself to poke the fuse out through the through holes. With it free, I pulled a spare fuse out of a different board, and sure enough, the spare is measuring correctly, but the original is showing open circuit. So the fuse was definitely popped. We'll toss the spare into place and solder it down properly, then check it in circuit one more time, and yeah, that's looking good. All right, the fuse has been replaced. It's all back together. What we're hoping to see here is for all 6 voltage rails to come up. That would be fantastic. And I want to see the DC on light on the front here stabilize. I don't know if it'll do that without a heavy load on it, but I think it might because we have a heavy load on the 5 volt, which is going to be our little automotive light bulb over there. So when I flip this switch, that light should come on, all fans should spin up, and we should get all 6 rails. The multimeter is on the +12 volt rail, the one that was dead. So hopefully we can see that one, and the other ones we already measured as fine. So let's do it. Fan spun up, light bulb came on. Still don't have 12 volts though. Dang, all right, so it wasn't just the fuse, or it popped to the fuse immediately, which means we've got a fault someplace else. All right, I think I've said this probably about 15 times, but I think we're starting to zero in on something. I'm taking a look at the control signal that's coming out of our 555 here. This should be a little pulse signal that is turning our 3904 on and off, that is controlling the pass transistor up here, but nothing is passing through. The fuse has been replaced. Q8 and Q7 have been pulled and tested to be known good, so something down here is incorrect. If we look at what's coming out of the 555, we have our little pulse there. That's excellent. But if we take a look at the next step along the way, we can see that it's just stuck low. This is looking at just after R112, which is a 4.7K. So something here is pulling it to ground. Blanking is not the problem because it's used by minus 12 and plus 5, and they're totally okay. Plus 12B shutdown is also not the problem. I've double checked that. It's okay. So Q23 has to be what's causing the problem here. If we look at the base of Q23 here, it's kind of hard to see. If I change the scale way down here, it's super noisy, but I think that's enough for Q23 to be turning on. And if Q23 is turning on, that's going to be pulling this to ground. So let's take a look at what's controlling Q23 here. And if we go back over to this one right here, that is the emitter, I think is the correct terminology, of Q27. It's the leg on the bottom here. And we can see that that's at 5, 10, 15 volts. So we've got a full 15 volts passing through Q27. Now let's check the base of Q27 here. And you can see the base is also 5, 10, 15 volts. The base is pulled straight up to 15. That's not great. So it seems like we've got 15 volts on every corner of Q27 here, which might mean that Q27 is unhealthy. Okay, it's been a couple of days since that last round of diagnostics with the transistor that I was looking at. I've been pretty much over this schematic beginning to end, and I think I'm finally starting to zero in on what might be the fault. I've said that far too many times. But initially what I thought was happening was that I thought that something wasn't controlling our pass transistors up here. So we replaced F1 and we have 35 volts coming to the other side of F1. The problem is that Q8 is getting pulled low and not allowing anything to pass. So I checked Q7. Q7 looks good. I went down and checked R31 and then checked Q10, the 3904, and this is where we kind of came into our little bit of trouble. And coming out of the 555, we do have a proper pulse coming out of pin 3. So that means that something here is pulling that pulse to ground before it gets a chance to meet the 3904. Q23 is kicking off and it's pulling that to ground, and that's not allowing the 3904 to trigger. So we followed Q23 back to Q27, and that's what we were just looking at, and turns out that is actually working fine. The difference between plus 15 volts and what we were seeing on the base is to be expected for a PNP transistor. That's enough to turn it on. We're just shutting this whole thing down. So we had to follow it even further back. And if we look at E2 here, I looked at the inputs of it and the output of it, and it is not causing the problem. So it's not a current sense problem. So we follow it back over in the other direction, and that brings us to the crowbar circuit. And in checking out the crowbar circuit, all of the components looked fine. And that was when somebody told me that I should be looking not at the steady state after it's on, I should be looking at what happens from the moment I flip the switch until the power stops. And that scope shot was very illuminating because it says that we are actually passing voltage through Q8 all the way out the plus 12 volt rail. It just runs away though. We are getting too much voltage, and that is kicking off the crowbar, which is shutting everything down. So the question now is, why are we getting too much voltage? The regulation happens with this little bit down here and the 555, and this is a very weird setup. The op amp over here on the right has an interesting voltage divider setup, and it will turn on or off depending on what the relationship between the two voltages coming into it are. And I checked most of the components around there, and most of them check okay, but they're in circuit, so they're probably totally fine. Now we know that the 555 is mostly working because we are getting a pulse signal out of it, but it is this setup on pin 6 that is a little interesting. We have Q24, which is a PNP transistor, then we have R111, D34, and R117. Now R111 and R117 measure bang on perfect in circuit. D34, I can't measure in circuit. I get something in both directions on it, but it could be fine, could be bad. It's kind of hard to tell while it's in circuit. And the same goes for Q24. I measure some funky things on Q24, and one of them is actually a little bit more of a red flag than D34. And let me zoom in and show you what I'm talking about. Now again, this is in circuit, so this could be totally wrong, but I'm gonna try and check this little transistor right here. And one way of checking that is you can use the diode test on your multimeter. And with a PNP, I should be able to put the black probe on the center pin here, and I should be able to go to either of the other pins and see a diode drop. If I go to that one, I get 0.651. That's kind of what I'm expecting. And if I go to this one, I don't get that diode drop. That's a little strange to me. There should be a diode drop between a base and collector as well as base and emitter. And we're not getting that. We can also check it the other way here by putting the red probe on the base here in the center, and I can check in this direction. And again, I don't get any diode drop that direction, but I do get diode drop in this direction of 1 volt. Now again, this is in circuit, so that could be totally expected. But the fact that we aren't getting a diode drop here is that's a little strange to me. So maybe this PNP has given up the ghost, and what that would mean is that we're not getting the appropriate voltage on the threshold pin of our 555, which means that it's not going to regulate appropriately with the signal that's coming in on the control pin, pin 5. So if that PNP is bad, it could absolutely cause the problems that we're seeing. All right, PNP's been replaced with a 2907, I think. It's just kind of what I had on hand. It was a generic PNP. I think that should work just fine. I'm skeptical that that was actually the problem. I'm betting that there's something deeper going on, but I'm kind of running out of avenues. So let's go ahead and give it a test. We'll flip the breaker on here. Then we'll flip the main power switch on here. That was totally it. 12 volts. We have 12 volts. Yes. What a relief, man. Just. Oh, all right. I've been going hard on this power supply for this thing, and boy, it feels amazing to just climb that hill and get to the top. At least for now, it all seems to be working, but what an interesting failure. We didn't have anything wrong with the big pass-through transistors or any of the regulating ICs or anything like that. It was just a simple PNP transistor that, as I understand it, is giving a regulated voltage to the threshold pin of a 555. This is an incredibly low current situation. There should be absolutely no current moving through this at all. And yet somehow that PNP went down. What a journey. All right, so what's next? Well, we're gonna start plugging cards into it and see how it handles a proper load. And well, we're gonna do just the CPU and memory cards, and this is just one of the CPU cards. This is gonna be about 8 cards in total. When I said this was a non-LSI machine, I absolutely meant it. So we'll take a look at each card as I plug it in, and maybe we can figure out what they're doing. Then we'll plug them all in, flip the switch, and hopefully nothing goes up in smoke and it all looks good. Okay, we're gonna go for the bare minimum setup here for initial testing, just the CPU cards and 2 memory cards. And we're gonna start with this one. This is an M7094, it's called the Data Path Module. And the manual says it does arithmetic and logic processing, shifting of 8, 16, and 32-bit data formats, byte swapping and sign extension of data, general register storage, and status information. And we can actually kind of confirm that with some of the ICs on here. There are 4 74S181s. These are 4-bit bit slice ALUs. We have some 93422 DC ceramic ICs up here. These are 256 word by 4-bit high-speed static RAMs. And then down here we've got 3 real big N82 S100s, and these are all PLAs, or programmable logic arrays. And hopefully those are all okay, because those are probably going to be the most impossible things on this board to replace. Next up is the M7095 control module. This one contains the control store proms and logic to decode and execute the PDP-11 instructions. It also contains the system clock, power fail, auto restart, boot control, and trap handling logic. And looking at the far left here, we have a bunch of AM27S181s, or equivalents, and these are 1024 by 8-bit ROMs. And then right next to it, we've got more of these N82S101s. These are, again, PLAs. There's a lot of hope riding on all these being good. This is the M7096 multifunction module. It contains an 8085 CPU, which I find absolutely hilarious. Has 2 serial lines, a line clock, and all the related logic. The serial lines are for the console terminal and the TU58 tape drive, and the 8085 enables execution of all the console commands. And we can actually see that 8085 right up here in the top left. This is a full-fledged 8-bit microprocessor. Right below that, we have a bunch of DM87S185s. These are 2048 by 4-bit programmable ROMs, or read-only memories. And then all the way over here on the far right, we've got some 6402s. These are going to be our UARTs, or Universal Asynchronous Receiver Transmitters. These are the 2 chips that are doing the serial communication to the console terminal and the TU58 tape drive. Next up is the M7097 cache memory module. This contains 8K of high-speed static RAM cache memory to decrease processor to memory read times. The memory is located in the most commonly accessed memory locations, and it's a directly mapped memory cache with write-through facility. I got all that lingo out of the manual. I don't necessarily understand what all that means, but I do understand that over here on the far left, we have a bunch of 2114 chips. These are not socketed, but these are all the 1024 by 4-bit static RAM chips that make up the cache memory, and this should make the whole machine move a lot quicker. But other than that, it's just full of a bunch of 7400 series logic chips to, I guess, interface all of that with the rest of the CPU. Rounding out the CPU here, we've got the M7098 Unibus interface module. This provides all of the logic which allows the processor to access the Unibus, and it also has bus arbitration logic for interrupts and NPRs, boot circuits, and buffers for PAX data lines to and from the processor, and it contains a map that allows for DMA between main memory and peripherals. And it's mostly just a bunch of 7400 series stuff, except for this row of big fat chips that we got right down the center. There are 2 different types of chips in here. There are 93459, that's going to be these 3 over here. Those are more PLAs, hooray. And then over here we've got 93419, and everything I've found on these say they are 64 by 9-bit high-speed static RAMs, which is a really strange configuration, but the access time on these is like 45 nanoseconds, so those are booking. And then finally, I'm going to put in 2 of these. These are M8722 ECC 256K memory modules, and they're pretty much what they say on the tin. There's a boatload of 4116 dynamic RAM chips over here. These are 16K by 1-bit DRAMs. Access time on these is a lot slower, around 500 nanoseconds on these than those high-speed static RAMs that we were looking at. But these are a lot cheaper, and you can fit a whole lot more of them on one board than those big honkin' static RAMs. Now this board uses the +12, +5, and -12 of the memory portion of our power supply, and so this is really going to put a bit of stress on that power supply. We'll see how it holds up to it. With 2 of these in there, that's going to pull some current, I think. Okay, processor and memory fully in. I did check the memory for shorts across all of the power rails because there's a lot of little tantalum capacitors on there. There were no shorts obvious, but that doesn't mean that one of those tantalums won't short out as soon as it gets power. Hopefully, though, that doesn't happen. What we're hoping to see here is for all the fans to come on and for DC on to stabilize down here. So, here goes. All the fans are on. DC on, looks like it's stabilized, says run. I think we're okay. No smoke came out of anywhere. I think that's powered up. If we had a terminal connected to it, we might be able to see something happening. The final piece of the puzzle is this card right here. This is the M7090 console interface module, and it does exactly what it says on the tin. It interfaces with the console. The front panel plugs in here, the TU58 drive plugs in here, remote diagnostics plug in here, and this plug here is for the console terminal. Everything else on here is just kind of buffers and level shifters and everything to support both RS-232 and 20 milliamp current loop. Now you can see that this is not a standard DE9 plug. It's a specific ribbon cable that's got to plug into that. And I dug through my stash and I think I found the right cable for it. This is it here. It says this side up has the correct key in it, and this should just plug straight into here like that. And the other end of that has a DB25 on it, so maybe this will work. I don't know. We're going to plug it in and give it a shot. To give this a test, I'm going to use my trusty ADM3A here. I've got it set to 9600 8-in-1. I have no idea if that's what the PDP-11 is set to, but we're about to find out. So we'll go ahead and flip the switch here. Hopefully we see something show up here. If I flip the... Nope, nothing at all. All right, I've confirmed the setup on the 7090 and the 7096. These are the two boards that control whether it's doing RS-232 or current loop. It is set to RS-232 9600 8-in-1, which my data terminal is also set to, but I didn't have a bus terminator card in there last time. So I've got a M9302 bus terminator in there, and I've got a bunch of knuckle busters down here that should be moving Grant continuity lines over to that. So hopefully that's the problem, but there also very well could be something more sinister lurking in these cards here that's preventing it to come up. But let's flip the switch and find out. Yeah. Our run light does not come on and stay on. It just comes on and then kicks off. If I hit boot, it turns on and kicks off again. Dang, we got another problem somewhere. Something deep is going on here. All right, I think I may have found a pretty important problem, even though it's not really that big of a deal. I'm pretty sure I need a null modem cable to go from the 9070 up there to my data terminal, and that cable was not that, and I don't have a null modem adapter. So I had another one of these cables, which is built in the same way, and I just modified it to switch RX and TX around, and that should get the job done. I've got my Terminator card in there, and I've got my continuity cards in there. This should work. Please work. I'm gonna flip the switch here and we'll see what happens. Console V3.40C program. It works. Yes. Well, my ADM3A decided to die, so we've moved over to my Rainbow 100. This is actually the end use case here. This is the terminal that I'm going to use with this 1144, so this is good, I guess. So we'll go ahead and hit T here, and I just want to make sure that we are set up correctly for the appropriate speed here, and we are not. There we go, 9600 baud. So we'll come out of setup here. Now let's turn the power supply on for the 1144. There we go, console V3.40C program. I can't do anything from here. No matter what I type, nothing happens. But if I hit Control P, then we can get into the console here. And there's a couple interesting things we can test here, which is illuminating a different fault that we have. First of all, I can do T here for a self-test. I don't know, I guess that passes. It just does that over and over again. But if I try to do anything else, like I tried to boot from here, which you can do by typing B and then whatever you want to boot from, like say DX0 here, it says halt CP. So if I flip the halt switch on the front of the machine and I try that again, DX0, still says halt CP. It should be halted. If I type H to halt the CP here, I get failed to halt. So I think my switch on the front that is supposed to halt the processor is not functioning, and then that means that the amount of things that we can do here at this prompt is very limited. If I do I to initialize, it says halt CP. If I do S for start, halt CP. So I think what we're gonna have to do next is we're gonna have to dig in deep into that front panel and figure out why it's not halting the processor, or why we can't halt the processor at all. It might not be the fault of the front panel. So we got an insane amount done today. We actually saw life out of this machine. We are so close to getting this thing actually running software off of some kind of drive, floppy or hard drive, like that big Fujitsu Eagle. So in the next episode, we're gonna try and get it halting properly. We're gonna try and get it doing stuff, trying to boot from things, and then maybe we can start plugging more cards into this to see if we can get it to actually do some pretty fancy tricks. But this is epic. We started this episode with this thing totally dead, not being able to run anything, and now check it out. It is properly running. That is awesome. So this would not have been possible in the slightest without a massive amount of help from everybody over on the Discord, namely Coley. He's been a huge inspiration because he's battling through an 1105 and an 1134 restoration of his own, and he's been really inspiring me to dig in deep on this. Also, Mitch, if you're watching, thank you so much. You hooked me up with a lot of really epic stuff, and because of that, we're able to get some really exciting stuff going. And we have a huge number of people that have been contributing to help me get pointed in the right direction on this thing, and it has been an absolute journey. So thank you all so much, and thank you guys so much for watching, and I hope to see you all in the next episode.